Good afternoon, good morning, wherever you are. Thank you for joining this TDL session on AI hardware, the challenges and opportunities. A really fascinating and very timely subject that doesn't get as much attention as it should do. So I'm very much looking forward to listening to our distinguished panel, led by our TDL Strategic Advisor, Claire Vishik, who will moderate for the rest of the afternoon. Thank you. Over to you, Claire.
Thank you to our distinguished panelists for joining us today. I am getting a lot of questions about hardware capabilities in the AI space, not just traditional AI space that enables LLMs that probably everyone in the audience is familiar with, not only about specific customizations by hyperscalers for this hardware, but also in such areas as automotive and IoT and generally edge and even on device processing associated with artificial intelligence and related hardware. These questions are about everything from transition from brute force to more efficiency, greater customization, to trends in architectures, to implementation of security in other areas that inevitably come up when we talk about it. It is also about the new technologies that may suddenly, not suddenly, but eventually get prime time, such as silicon photonics, that has been much more prominent today in terms of strategic deployment and more commercializable implementation. So these are all the areas that we are going to discuss today. We are fortunate to have a distinguished group of panelists with different expertise that are joining us today. I will introduce them very briefly. We have Helena Handschuh, who is the technical board advisor at QuSecure and SCI Semiconductors. We have Rahima Mohammed, who is the semiconductor technical advisor at WinC for the AI. We have Sohail Salehi, who is an assistant professor of electrical and computer engineering at the University of Arizona. And finally, we have Silvio Vaciano, who is the director of trusted security systems at Huawei, working in Munich. With this brief introduction, and you can find more about our panelists online. Let's start this discussion. To begin with, let's talk about your general view on AI hardware. Where do we stand? What the most meaningful innovation is? What do you think is the most important in this space and its evolution? We will start with you, Helena. What do you think?
Yeah, thank you very much for the introduction, Claire, and thanks for having me on this panel. My background is security, so of course, two things are very important for AI hardware in the AI world: processing power and memory bandwidth. But given that my background is security, I'm going to talk about security. I'll let others talk about the other most important aspects. So in terms of security, as soon as you talk about doing something with a lot of data, handling a lot of data, and then making decisions based on that data for things to happen next, immediately you think about, okay, how is that data being secured? How is it stored securely? Where does it come from? How do we make sure that nobody interferes with what the training is doing? Nobody interferes with the decision that's made when you inference a result. And so crypto comes up first, and there's a few things here that can be done, namely things like something called fully homomorphic encryption is one direction we can think about. I think there'll be a lot of innovation in that area. A second innovation area is everything relating around roots of trust and how to secure the computation environment itself. And the third one, which may be a little bit from a different perspective, different angle, is something called memory safety. Lots of attacks these days, cybersecurity attacks, come from the fact that people just take over the system remotely. And that's going to be a big issue for things AI-driven, such as, autonomous vehicles. Imagine a whole fleet getting taken over and doing whatever. So these are my three different items that I think are most important and where we will see a lot of innovation in the future.
Absolutely. And those are very important areas. You mentioned homomorphic encryption, which has become much more prominent today than it had been even 2 years ago, with new approaches, new commercial solutions developed. Do you think it's broadly applicable to such environments as LLM, or do you think it has a narrow scope within this system?
I think we started off with trying to secure everything that related to the computation, the inference, and the result itself. But not so much had been done on the training part and kind of taking all the data and making sense of it. And so as you dive deeper into LLMs and things like that, you will need more of it in that area, but it's also much more difficult to handle. So there's still a lot of improvement to be done in terms of being able to process that much information at the same time and make sense of it. So the more we go in that direction, the more power we need, the more we need to be inventive about the models that are going to be used to address the space. And all of that is complicated math. And we're not quite there yet, but we're working on it.
Thank you. This certainly is a very optimistic, daring view on the scale of protection that we can apply to artificial intelligence. And it certainly is encouraging. Rahima, what do you think?
Thank you. Thank you, Claire, and thank you, TDL, for this invitation. So, my background is actually in thermal design, advanced cooling, and power thermal validation of data centers and client SOCs. So now I'm actually on the semiconductor technical advisor, so serving in Vinci, where we actually build physics intelligent simulation for advanced semiconductor packaging. So my area would be, my lens would be much more on the thermal and the packaging wall that we are seeing. So I think I'm going to talk about three different things. So the first one is we are kind of in a moment where AI accelerator TDPs have crossed this 1 kilowatt and are projected to reach about 4 kilowatts by the end of this decade. So it's really not a scaling, it's not an incremental scaling problem. It's actually a fundamental physics problem. So you are moving from air cooling to liquid cooling, as you might have seen everywhere. But in the middle of all of this, the architecture is changing very heavily, which is changing from monolithic to the shift to the 2.5D and 3D architectures, which the industry needs because of the continued performance scaling, but it's entirely new technology that requires understanding of the thermomechanical challenges, thermal coupling between the heterogeneous dyes, CTE mismatch, driven warpage, vertical heat accumulation in the HBM stacks, etc. The second problem that we have to think about very carefully is this shift that we are going from training to inference, which is where moving from flops discussion to token per watt and performance per watt. And that's where interference at scale is a cost per token problem, not a peak flops problem. So that's the second one. And the third one, which is very interesting, is the efficiency. But what I mean by this efficiency, it's just not electrical efficiency or a thermal efficiency or a packaging efficiency, but actually the speed at which you are uh, simulating and designing that efficiency. So the ability to design, simulate, and validate complex chiplet packages at this manufacturing resolution using this physics AI approaches rather than legacy chiplet or compact models, actually compact models, that will determine which company can bring the next generation AI hardware to production on a competitive timeline, because time to market is everything, and that's the toughest problem that you're going to see. So those are my three.
Uh, uh, this is a very interesting view, and it's rarely mentioned that uh, the timeline in something like fundamental foundational hardware is extremely important. It's typically said that the life cycles of product development and product existence has accelerated to a point where it is extremely difficult to track, and implementation and deployment become much more complicated. But of course, in reality, transitioning to hardware that is based on fundamentally different principles is continues to be extremely slow, and perhaps we cannot afford it anymore. What do you think is the role of fundamental science in speeding up the way towards newly defined hardware based potentially on new or evolved principles?
Excellent question. So let me unpack it. So take an example of uh, um, any of the OCP board today, the Open Compute Project board today. You have the CPU coming from one vendor, the ASIC coming from another vendor, HBM coming from another vendor, the DIMMs coming from similar or the other vendors, the boards coming from other vendors. Nowadays, and actually, the problems arise at the interfaces. And the crosstalk of one CPU or one ASIC is impacting the HBM. So, in order for you to do this, all of these have to kind of you have 5 to 9 different vendors and can even have more, so n parties involved. So usually now what happens is we do our own stuff and we actually put a lot of margins, and that's a lot of dollars or a performance on the table. And that's also a lot of actually time to market also gets delayed because we find these issues much later in the cycle than during the design stage. So one of the things that we have been working in Vinci is in Vinci 4D, one of the things that we are looking into is this manufacturing resolution, trying to bring all of that in the same physics. But actually, to bring multi parties, you need something like a physics aware coupling transport protocol. That's what we have been proposing. And it needs to become open. And of course, there's a huge problem of because we have competing companies, you don't want to be sharing the IP. So, how do you still manage this and without actually sharing the IP, but getting it to a point where you can actually simulate all of the physics at the same time? So we have been proposing a standard called PACT, which is the Physics-Aware Coupling Transport Protocol. It's very similar to what happens in the network industry like BGP, where you only talk about interfaces. I need to shake hands at the interfaces, where you probably, we call it Robin boundary conditions, which is the interface is defining the temperature, the heat flux, etc., bringing all the interface boundary conditions carefully, but not sharing the rest. So we have done some initial prototypes to show how to work between the companies across the different tiers of the semiconductor companies and across the different industry in a very careful way so that you don't share the IP, but still work through this process. So that's the methodology that we are talking about.
Thank you. Thank you very much. That's fascinating. It certainly has been a dream for all of us working in hardware-related technical areas to create greater coherence at interfaces without excessive disclosures. And hopefully we'll come back to this topic later in this discussion. So, Kyle, what do you think about the space and its evolution?
Well, first of all, thank you for having me. The comments I make, it's going to be primarily focused on what I do research primarily on, which covers AI-enabled hardware design and security, edge processing, and using emerging post-CMOS emerging technologies to build AI hardware or the next generation of AI hardware. I mean, there's a lot to unpack here, right? So it's a very interesting topic. It's a very timely panel. Thank you for organizing it. So I believe we are going to see a big shift going from, data centers, GPU, and data centers back to edge devices. This is definitely backed up by the physical limitation that is power consumption. Energy efficiency is key here. Rahima put it really perfectly. I couldn't add to that in terms of thermal management. That's going to become a big problem, especially as we go towards 2.5D, 3D integration where you're stacking chiplets, right? So that's thermal management becomes more and more important. So energy efficiency is a big issue, no doubt. But I want to go back to Helena's point about security because as we move towards edge devices, then we are also going to see a big shift and a lot of attack vectors open up with respect to security and vulnerability of edge devices and AI running on the edge. Now, imagine you spend a lot of money, millions of dollars, to train AI models, and you cannot take those AI models and port them directly to your edge or hardware, right? You have to do some sort of compression, some sort of modification, and then once you put it on the hardware now, the hardware we have seen, like in my research, we've shown that there are many attack vectors or vulnerabilities that we can, there's exploits that we could leverage and reverse engineer the parameters of the AI models running on the hardware. So this brings up the very important question of when are we going to move towards security by design for AI hardware? So that's something that I'll be highlighting more in my conversation today, especially now that we are moving towards shifting towards neuromorphic computing and trying to step away from von Neumann architectures and the bottleneck that it provides. We need to think about, okay, when we are designing the next generation of AI hardware, let's think of security right now because I believe one of the major limitations that we're going to see down the line in the future is going to be, of course, excuse me, power efficiency, security. These are the main two issues that we're going to see. And of course, there was a point about who is going to design these chips, these AI chips, because we see a huge need, especially in the United States. I'm sure it kind of goes around all over the world. We have a big need for the workforce in chip design. And from my perspective, what we are seeing is a lot of companies are coming to the scene that leverage generative AI and large language models to design hardware. And we see a significant interest in that area because companies will come in within 2-3 months. They raise a lot of money to take it to the next level of their product. So that rapid pace of development is very interesting to see, and it gives us some trends, right, to look into. And one last point is about reconfigurability I want to highlight. we see models change from week to week, if not month to month, right? So if not day to day, sorry. And that means that the hardware, if it's an ASIC hardware, you spend a lot of money to design that ASIC, to fabricate it. There's the time, and then the new model comes out, your ASIC becomes relatively obsolete. Now you need some sort of reconfigurability to the hardware to be able to adapt at least a little while post deployment to adapt with the new models. And that's also another point that I'll be highlighting in my conversation today.
Thank you very much. Very interesting points. Certainly, energy efficiency that is talked about a lot, but probably not paid as much attention as it needs in terms of the design could be a key issue. I still remember how, for example, software-defined radio waited for its commercialization for something like 2 decades and maybe even more because of this issue, because of transitioning from band to band was very energy and resource intensive, and there were no resources and small form factors that could support this. And I think similar things are going to happen to potentially delay edge and on-device AI. Maybe 10, 12 years ago, I heard a series of fascinating talks about near data processing on device without transferring it to some kind of aggregation point, which requires a lot of energy and resources. It was an interesting idea, but it was not at the time implementable at the edge. Do you think it could be implementable in the near future based on your work?
You're definitely moving towards that. So that's a great question. And we see the shift, right? So, what we've seen in the promise of these new technologies and emerging devices is nearly 100x improvement in energy efficiency for doing the inference operation. So training is another beast that is definitely much more challenging to do on the edge when you have resource constraint, not just, you have limited power and you have a budget for your power consumption based on the battery, for example, if it's a battery device. And that's one aspect of it. Another aspect is the resources of the hardware. So your edge might not be able to perform all those matrix multiplications that are required for like a transformer model. And with all the parameters that we're talking about, you cannot bring down that billion parameter model and sit on the hardware. So you have to, as I said, compress and do some sort of modification to it. Now that model is going to be slightly different. So you're already sacrificing some accuracy, and the hardware could have some reliability challenges and issues. We see, for example, if it's deployed in space as a harsh environment, you potentially have some faults that are going to happen. And these are not necessarily attacks. These are random faults because of the environment that is happening. And those will have a bigger impact on your accuracy or ultimate accuracy of the model that is running on your hardware. So there's like those challenges that we need to also consider. But overall speaking, yes, I would anticipate in the next decade, for sure, we're going to see a big shift towards models that are, I mean, we see it now, right? So I would assume that within a decade, it will be more mature. But we see models being run on edge devices, and they're being optimized through co-design of algorithm and hardware. And that's the term that I keep hearing right nowadays with co-design. And that's big interest also from funding agencies. They want to see this co-design because hardware limitations and these algorithms, the algorithms need to converge somehow. And to do so, it's to think about a co-design approach. But I'm hopeful within the next decade, we will see a lot of that coming to market.
I think so too. Thank you very much. Very interesting ideas, and certainly we will return to them in the rest of this discussion. Silvio, what is your view on the space?
First of all, thank you for an invitation to such a great discussion. I think indeed. It's one of the spaces that we should be talking more about when we talk about AI. So, from my perspective, I have a background in system security, so my focus is on leveraging hardware to secure the rest of the system. So I'm inclined to talk about the security dimension. However, this has been talked quite extensively by Helena and Sohail. So I'll just pick up very quickly some points from security that I find important, and then I'll try to also look at the other part of system security, which is the system itself. So um, in terms of security, I think Helena mentioned very well that roots of trust are now becoming uh, ubiquitous, right, for the computing infrastructure, for the hardware. Uh, what used to be the realm of the CPU is now we find it in every computing unit, small or big. And at the same time, also, Helena mentioned the memory safety concerns that appear once we have computing happening in different types of hardware. I think this is in particular a concern with these accelerators that have enabled the AI, let's say, progress that we've been experiencing in the last decade or last couple of years. So I think they are a bit understudied. Everybody is focusing, like Sohail mentioned, on performance, and we still wait for that security by design moment. I have my reservations that we will ever see a new category of products that will start with security in mind, because unfortunately, security by itself doesn't sell. Nobody buys products just to be secure. Yet that's what we always have to fight with soon after they become even mildly successful. So yeah, I think these are all very good points. But I would mention also some observations about the system. So the hardware itself, how does it look today? So I think when we talk about AI hardware, everybody thinks inevitably of GPUs. In fact, there are people who call GPUs almost everything that accelerates AI. But I think that's just one side of the story. I think GPUs dominate today. They are ubiquitous. They are the unmissable execution unit from phones to laptops to data centers. And what's interesting is that it's not just the hardware that is ubiquitous. In fact, many people argue that the major success of GPUs has been their software mode. So the fact that it is very easy to use them, unlike more dedicated ASICs. So I think GPUs they have brought us here to benefit from this evolution of AI. But now I see two trends coming up. One is specialization. Of course, we see neural processing units and tensor processing units who are already very successful. And also, we see that even GPU vendors are looking to expand their computing unit designs with more specialized units. In fact, even GPUs, they are not just GPUs, they are a combination of many heterogeneous computing units. So yeah, this is, I think, one important trend. We see specialization driven by efficiency, cost effectiveness as well. But I also see a trend of what I like to call the absorption. So we tend to not talk about CPUs anymore, but CPUs are not dead. In fact, we could say CPUs are back with agentic AI. They are underpinning a lot of their success. And also, I see that CPUs, as they have been doing in the past, when there is a successful acceleration capability, they tend to accumulate it. So now we see accelerators for matrix multiplication that come into the CPUs, and in some scenarios, perhaps edge, we may not need all these accelerators to be separate heterogeneous units. So yeah, these are the two trends I see, and I believe that diversity and use case adaptation is still something that will evolve in the next couple of years.
Thank you, Silvio. Those are very important trends, and I agree that there is a movement from the focus on GPUs in this area to other capabilities, TPUs, accelerators, and of course, more specialized CPUs, especially for the edge. If we are talking about the areas of innovation, that are the most productive short term. What do you see? How can we support through innovation, hardware, software, co-design that you dedicated a lot of attention to in your intervention.
Indeed, we need to have a consideration of both the hardware and the software when we talk about AI hardware, AI infrastructure. So I think the innovation is like some of my colleagues mentioned earlier, will come from the efficiency improvements. So everybody is looking to reduce the cost per token when we talk about inference, and it's true that also. AI hardware has been a relative luxury for most companies these days. So having more efficient hardware and also that is cheaper, I think that will drive a lot of the innovation factors in this space. Uh, I would also mention that besides the actual computing units, innovation is happening also in the interconnect side. I believe scalability of different compute units to be able to be disaggregated in a data center or to be able to pool them in a large number of nodes. For example, we've seen interconnects announced that can support up to 1 million of nodes. I think this is what is driving today a lot of interest and a lot of innovation. This helps also to address challenges such as the memory wall, which we've always been familiar with time and time again. So being able to scale these interconnects, scale them up, make many nodes behave as one, or scale them out so that we have many sets of nodes that collaborate. I think this is going to drive a lot of the benefits that we will get in the next years for cheaper, more efficient AI.
Thank you. It's impossible to disagree with what you said. And Helena, you focused on security and how it can be implemented. There is always concern, especially when brute force is the most important component of an architecture, that security consumes a lot of cycles, that it costs sometimes as much as 40% of resources on a CPU. How do you think this issue can be addressed? How do you think it will be addressed in terms of innovation in the near term?
So I think this is a very interesting perspective because that's exactly what's happening, right? Security seems to be adding a lot of costs all the time. But I also believe that there's kind of very good news at the horizon here because something happened very recently, which is that a technology that's been existing for about 15 years, that's called Sherry, has recently been put in an actual chip and is now available for people to play around with. And this technology addresses security, memory safety, and is secure by design. So for Silview, there is hope at the horizon as well. So let me explain what that is. Sherry is a capability hardware enhanced risk instruction technology. That means that the hardware itself is now capable of giving you at least some approach and some notion of security in terms of, disallowing privilege escalations and managing the memory safely so that you can't insert, bad code anywhere, stuff like that. So it's built directly into the hardware. The technology is available, and you can combine with things like matrix multiplication accelerators, such as, not to name it, Google's new NPU, for example. All of this is totally open source. You can totally play with it. And by combining these things together, and going the direction of sharifying, which I don't think is a verb that actually exists, but I'm just going to make it up. Sharifying all the new things that come out, specifically AI hardware related. Now you have it by design, right? It's in there. So you know that in terms of cyber attacks, in terms of remote taking over remotely, for example, for autonomous vehicles and things that just run by itself and make decisions by itself at some point, you're on the safe side. So this, I think, is a little bit of a revolution. It's not really been done this way before. People have tried, but for some reason, one reason or another, it didn't work out. But this time, I think we're there. You don't have to eats 40% overhead anymore. It adds very little overhead because it's already in the hardware. It just interprets things differently. And there's no processing overhead, none of that really. And so that for me is really good news. Changes things.
It seems to be. What is the applicability, the key use cases for this?
Anything that you can think of that is connected to the internet where you don't want anybody to take over. So if you talk about edge AI, that's exactly what we're talking about, right? Things that can take autonomous decisions based on data that never leaves the device, that gets treated and analyzed, and decisions get made on the device using AI, exactly that context. Meaning you're on your own, these devices run by themselves and use Cherry capabilities to make sure that nobody else is going to take over the system. So that's a huge, huge market for applicability of this kind of thing.
Yeah, it's a huge market that will also require some level of customization that's easily achievable, but certainly considerable progress. So, Hale, what do you think is the area of innovation that is
Just one
pragmatic?
quick moment. I think Silvio had a point to add, maybe to Helena's. I'll let him speak
Okay.
before.
Thank you very much, Sohail.
Silvio?
Actually, I just
Right.
wanted to confirm that cherryfying is indeed a verb. We have been using it. I've heard other people using it, so it is indeed coming in the industry jargon. I think you made a very good point. Cherry is indeed security by design. What's even more interesting with Cherry is that in some cases you don't need to bear the extra cost for Cherry on top of the existing hardware because it may be able to replace some existing blocks. For example, in microcontrollers, in my group, we've been looking at whether we could, for example, compensate the need for an MMU with Cherry because we would not need to do the memory isolation with it. So yeah, Cherry is indeed an interesting technology. What I would like to see with Cherry and maybe with more hardware-based memory safety technologies is moving to the space of accelerators because it feels like it's such an empty space in some aspects in terms of memory safety, and research is only recently starting to look into what can go wrong there, and already there's a flourish of papers at recent academic conferences on this. And yeah, maybe Cherry is the answer, or maybe we can think also of something more specific for these very data-centric architectures like GPUs and PUs. And thank you, Sohail.
It's impossible. It's impossible to disagree with what you are saying. Maybe the opportunity is in both in Cherry-like approach and accelerators. Both are promising. Both have still a lot of work needed to do to make it highly commercializable, but it certainly is considerable progress. Thank you very much, Silvio. Sohail, what do you think?
Yeah, so I just wanted to, thanks Helena for, all the great points that you made, and of course Silvia for following up on that. From my perspective, the challenge that I see is with hardware, going back to if you're designing, if it's built, if it's not reconfigurable, you cannot change it, and that's also a security concern as well. You always, if there's a vulnerability you're aware of, if you're a weakness in the hardware that you're aware of, you can, fix it potentially a lot of the problems at the design time. But at the end of the day, when you get the chip, there's a lot of physical vectors of attack that could, be applicable in that scenario. That at that point, if you find a vulnerability or weakness in your hardware, that means a whole redesign process and remanufacturing, which is a huge cost when we're talking about semiconductors. So that's a big challenge that I see moving forward, because one of the things that we are highlighting with AI hardware and acceleration of it, as I mentioned earlier, is moving towards new technologies because we are reaching the limits, right? With the Moore's law, we see the scaling trend is going towards new materials. There's a lot of big push for new semiconductor technologies that could address some of these challenges with respect to the memory wall, the power wall, and so on. There's a lot of concepts of in-memory computing. That's one of the aspects of research that I'm working on. And these new designs introduce new threat vectors that we didn't have to think about before, or they're not necessarily the traditional threat vectors that you're used to see. And that a lot of when we talk about security, the lack of these unified metrics that you can use to say, okay, there's guaranteed security. There's no way, right? Because you can, of course, secure against known vulnerabilities or weaknesses. And, of course, if it's secure by design, there is some sort of guarantee. But that guarantee falls apart if you change the threat model, potentially, right? So that becomes another topic of conversation. What are those threat models that we need to think about when we're talking about AI hardware? And put forth kind of like in the standard fashion, certain way of thinking about when you go about designing an AI accelerator, what are those threat models that you need to think about? But again, things evolved. So AI algorithms evolved with hardware evolves with it, and that means the threat vectors also evolve. So to me, it's always been a cat and mouse game. So we're not going to solve all those problems, right, overnight. There's a whole research happening in all those areas that I mentioned. But we're making progress, which is really exciting. Go ahead.
We're certainly making
Oh, no.
progress. It's also true that the threat landscape evolves in a visible way, at least faster than hardware. That creates a lot of challenges for the designers, people who deploy, people who are faced with issues on already deployed hardware. Something that probably we have a dedicated discussion about how do you address that in the hardware space. Very good points. Um, Rahima, what do you think? What are the areas of innovation that are especially important?
I surely want to answer, but looks like Elena wants to say something. He has.
Just before we move on to the next point, I think to echo what Sohail was saying, that there's different areas in security, and one of them is very clearly around temp resistance and challenging the physics of new technologies. Because if you talk about new physics or new methods of doing the computations at close to the electrons, right? Then you have new side channels, you have new temp resistance issues. So as soon as you put the object in somebody's hands, the attacker has a very different threat model. And these are all things that we still need to work on. So I think when you see challenge, I see total opportunity, and I love it. Thank you for bringing it up.
Thank you. It certainly is an opportunity. It's a very difficult problem to address, not just in hardware. The hardware issues are especially complicated, right? How do you anticipate threats enough in your architecture to protect against a wider range of anticipated threats and also non-anticipated threats? That had always been a question that no one could answer, but a great research area. Thank you very much, Helena. Rahima, what's your view?
Yeah, so at my end, I think I'm going to go back to kind of the details of the power discussions as well as the details of the cooling and simulations. So on the energy efficiency approaches, I think I look at it as three different vectors. So the first one is kind of at the architecture level, where you thinking about sparsity aware computation, quantization, kind of the mixture of the expert models that activate only the parameters needed for a given input. But the second one is actually at the packaging level, which is where advanced cooling that allows chips to run at higher power without throttling will kind of, whether you're talking about direct to chip liquid cooling or you're talking about two-phase cooling, uh, that'll actually help us to make sure that the chips will not throttle, give us better power, and it will also make it more reliable. So while security is very critical, reliability is going to kill the details unless you think about from the architecture level. And then I think the big one is at the simulation and the design phase. This is where we have to kind of think about changing the whole methodologies, the process that we have right now, to something where you are not doing after the fact, but you are doing, and I think it was Suhail talking quite a bit about the co-design. Co-design for this era is so critical, mainly because if you are going to think about at the interfaces, usually what we are doing is we finish the design, we give it to somebody else, et cetera, et cetera. But right now, in order for us to achieve this, so there's a lot of things that we're working with at least 5 different leading companies about how do you do this co-design? What kind of things, tools can you come up with where you can, uh, and the simulation tools have not kept up with this big change that's coming in. And so, how do we change the simulation methodologies? Use AI, lots of pre training, and the details to make sure they become fast enough so that you can bring all these capabilities of manufacturing resolution to a level where you can do thousands of simulations, look at the what ifs, and see where the breakdowns are, or even what design criterias are actually better for us than really going and finding the issues at post silicon or at production. So those are some of the specific details. And the memory, I think Suhail touched on this, which was stacking of the dies. One of the very interesting examples that we are working on is because the base die does not have as much of IPs as, and it has probably some space available. So there's a lot of discussion of custom HBMs where you bring some of the IPs from the ASICs to the custom HBM and on the base die. Of course, that has an impact on the whole stack. If you're talking about stacking 16 dies one on the top of each other, how do you cool it, but also move this, make this as a design at the design phase? Like, what parts can I change? What parts can I bring from here? So it has to be a co-design strategy. Is I think will play a very big role in kind of the next generation.
Absolutely. And if you listen to the CEO of the large companies in this space, AMD, NVIDIA, Intel, you could see that there is a lot of interest in bringing AI into the development process as an efficiency tool. Having tried using AI for various simulation use cases, I can see that the technology is not mature yet. It requires a lot of work. This is a
So I got
situation
excited
where,
to join after leaving Intel. I joined Vinci was because
right.
I saw that they were about 1,000 times faster than anything else available in the market. So that got me very excited. But the fundamental
Mhm.
reason why they are 1,000 times faster or can do a lot of things faster and with a higher fidelity, uh, actually almost 1,000 times higher fidelity as well, is because they're doing a lot of the details of the simulations at the earliest, continuously training the models separately. And the reason why this technology is so good is because it can work in the customer environment behind the firewall. So you don't need the customer data to train. You're constantly looking into all the capabilities of the physics and training the models on the various geometries and coming up with some initial details. So that whenever you're thinking about these very critical physics problems, there's a lot of initial estimate. In this case, the reason why it's so much faster is because to begin with, the 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 AI models are already giving you a very good initial guess to start with. And that's what makes it much faster. So we are already seeing this, and we are deployed at 5 different companies, and 18 other companies are actually have evaluated us.
Oh, thank you. We certainly need improvement in those tools to support realistic approaches to simulation, to speed up design. And it's good that there are now realistic opportunities to implement it in both limited and more extended scale. Let's now transition to the last question in our discussion. Uh, the impact of innovation. Where do you think the area is going? What do you think is going to be the most important? We mentioned a lot of areas from co-design to approaches to cooling, to reliability, to security concerns, to new approaches to security, to interconnects, and so on. Where do you think the innovation will focus? Do you think there will be competition for resources with other prominent areas like post-quantum cryptography and related areas? What are your concluding remarks on the topic? And Silvio, we'll start with you now.
I believe in terms of innovation and further directions, at least from my area, which is security, looking at the hardware, I'm pretty optimistic. I believe we live in a golden era of opportunities for making hardware-based security more present in AI hardware. And why is that? It's probably the best to just mention what was announced by Anthropic 2 weeks ago, their model that can reverse engineer everything, that can not only find vulnerabilities but chain them and exploit products end to end fully autonomously. And I think that we are now at a stage where we can no longer complain too much about the security cost of or the hardware cost of security. So I think we can rely less and less on software to just be able to protect itself. So we need to finally consider how we can take advantage of security techniques that have been promoted and researched since years, but couldn't make it due to the cost. I think we will have no more options. So yeah, hardware innovation cannot slow down in my perspective, and I'm excited about this. Yeah, that's my
Yeah,
ending optimistic view.
it's great to have an optimistic view, especially in light of Anthropic's announcement. It is true that if reverse engineering is really as reliable and successful as they claim, the fact is that those vulnerabilities were there already. They are not introduced by Anthropic, and they can be found and resolved in future design approaches. On the other hand, however, we have an installed environment with those vulnerabilities that become suddenly much more exploitable. So it's an interesting time, and certainly is, in a way, a golden opportunity for better hardware and especially more secure hardware. Thank you. It's good to have an optimistic view. So, Hale, what do you think? Are you optimistic? Where are we going?
I mean, surely I'm optimistic. Uh, I'm not like Silvio. I'm very optimistic in terms of the direction that we're going, and of course, as I said, we cannot solve all the problems overnight. We haven't solved all the problems of the previous technology right now, right? So we're still working on it, and that's going to be a constant battle that we have to take on. And as Helena said, embrace the challenge and see it as an opportunity for innovation. And I think there's a lot of opportunity for the next generation. Also, I tell my students that this is the time to be doing research on these topics because it's very exciting, and you can actually solve really big issues and have a significant impact. Kind of trying to wrap some of the thoughts in my head, going back to what Rahima said about also this co-design that we've discussed earlier. We see a shift from going from design technology co-optimization to system technology co-optimization, or STCO, and that's kind of going back to what we said about chiplet integration and you have systems where 2.5D, 3D packaging, and then the software comes on top. So there needs to be a whole system optimization, system and technology co-optimization. So that aspect is definitely, we see more of that. I'm sure moving forward as well. Another trend that was put out by TrendForce in a projection, we see, as Sylvia mentioned earlier, we see a big push towards more custom solutions, about like 45, nearly 45% growth in that market, where GPUs a little over 16% growth comparison-wise. So we see that big push. So I would say that will be a big, not, I wouldn't say change, but big growth in that area that we're going to see with custom hardware. We see this is primarily focused on bringing down the cost per watt, the cost per token, and improve sustainability, of course. So this is the trend, and we're moving in that direction. Of course, another aspect is funding, especially for research. That's something that I believe it's not that it's not there or non-existent. It's definitely has been more attention to this topic, and there's been more investments. But more so, we see that on private sector, not on the public domain. And that's not necessarily limited to the US, it's international. We did have the Chips and Science Act in the US, and of course, there was other initiatives similarly in the Europe that are encouraging focus, bringing a lot of focus back to semiconductor and chip design and manufacturing. But one of the things that I see, as I mentioned earlier, we need to advocate for these areas and encourage more talent and workforce to go and take over these challenges that we are talking about. I think we need more of that in the area, more excited, talented young minds that are ready to innovate, and then we need to bring more of them into this area and enable them, give them the tools they need to help us solve these problems. So I think that will be my thoughts moving forward.
Thank you. Definitely an outstanding thought. Hardware in general, its design and co-design and its security is a complicated area. It's not easy to create expertise in there. It requires a lot of training, and certainly a lot more needs to be done, from funding to new curricular, and hopefully that will happen. But I am glad you are optimistic. Rahima, what do you think? Are you optimistic?
I am deeply optimistic. Actually, very interestingly, I think just having been part of Intel for 27 years and we have lived through multiple semiconductor walls, whether it's the power array wall or the memory wall, the lithography wall. But each time the industry has found a way through, usually by changing the dimensions of the problem, by going from frequency scaling to multi-core, or from monolithic to chiplet, from air cooling to liquid. So kind of we are at that inflection point again because of suddenly all these changes happening at the same time, and why co-design becomes such a critical aspect. Now, the thermal and packaging challenges are real. There is no, but the good thing is, so is the innovation response, because lots of advanced cooling technologies are actually now coming in the market that were considered 5 years back, maybe exotic, but now they're mainstream. So I think the opportunity is for us to grab. And with this discussion of physics intelligence simulation is also making it possible to design, validate really complex packages in weeks rather than months. And I think Sohail touched on this. The CHIPS Act and the EU CHIPS Act are actually channeling unprecedented, very good public investment in the semiconductor R&D, which is a good thing and needs to be both for in all the vectors, both private as well as public. But what really makes me very optimistic is the talent and the energy I see in this space. So the convergence of AI, advanced packaging, thermal engineering, the security aspects, the reliability aspects actually has created the most exciting problem space in semiconductor engineering, at least in decades that I have seen. And the people solving these problems, some of them I'm very fortunate to work with, are among the most creative engineers I've encountered in my whole career. But very interestingly, I think the other important change that I'm seeing is suddenly you have a lot of customization, suddenly you have a huge amount of verticalization because of the problem we talked about, because uh, um, working between multiple tiers is extremely difficult. So there's a huge change or shift in the market because of this, because of those issues. You're seeing a lot more verticalization. And whether these markets will, lots of new markets are emerging. So whether it's the inputs at the edge or autonomous vehicles, robotics, scientific computing, in all these cases, they are just emerging like crazy, especially because of the AI. So I think if I'm not excited now, when will I be? So I'm really excited.
Thank you very much, Rahima. It's interesting that everyone is optimistic, excited about the future, even though uh, there is much greater visibility into imperfections of designs, much greater understanding of how different components work or don't work well together. It certainly is a different world coming up, and optimism is warranted, as well as probably some level of apprehension. Helena, you have the last word of the panel. What do you think will happen? Are you optimistic, and why?
Okay. Let's see. So let me take it into a slightly different direction then. About a year ago, OpenAI found the first memory safety issue in published code. And so by now we've seen that Anthropic, Claude can reverse engineer everything. So AI is being used to find vulnerabilities and stuff like that. Okay. But I think we should go more in the direction of, can it actually help us do something in terms of fixing vulnerabilities and doing better at what we do. So I think there's huge opportunity for AI to help us, do some software code reviews. Why not help in simulation, as we talked about? Also, why not accelerate verification, for example, in hardware by itself, right? We spend 10% of our time designing stuff, and then we spend 90% of our time testing and trying to verify that things actually work. So isn't this a huge playground for AI to help us as well? I think anything from hardware, verification, testing, code reviews, fixing vulnerabilities, use it as a tool to go faster in the actual part that takes so long. That's where I think we can do a lot of improvement and a lot of research. So
Love that.
it's an opportunity, yes.
Yeah, I think that will be a
absolutely.
conversation for Halloween. It's more spooky.
Probably. And maybe we should schedule one on Halloween, even if it's not a Thursday, to see if we can spook everyone. Thank you very much for concluding on this potentially cautious but also somewhat optimistic note. That was a fascinating discussion with a lot of food for thought, and I hope we will be able to continue it in the future. Silver, Sohail, Rahima, Helena, thank you very much for joining us. Thank you for sharing your thoughts. And now I will pass it on to David for final comments. Thank you very much.
Well, thank you, Claude. I said Claude. Thank you, Claire. I don't have the panelist. I got Claude on the brain. It's mythologizing
Right.
by language.
Mm,
That was a joke. That was a
mm.
fascinating discussion and very timely, and it would be great to come back to it in 6 months or later. Um, and your collective enthusiasm is quite infectious. So thank you very much for your contributions and a very positive discussion. And I look forward to seeing you all again.